I wanted to work through an example or work through a problem that involves a charge moving through a uniform electrical field. Actually, we're going to work the problem with a proton that moves through an electrical field, positive charge, and also an electron that moves through a uniform field, it's a negative charge. And we're going to think about the change in potential energy when the charge moves through the electrical field. We're going to think about the change in kinetic energy when the charge moves through the electrical field. We're going to think about the work done by electrical force when the charge moves through the electrical field. I partly wanted to work these examples or these illustrations because one thing that can be confusing, one thing that we can often get wrong, is the sign, plus or minus, of changes in potential energy or changes in kinetic energy or the work done by a force. And so we're going to work out changes in potential energy, kinetic energy, work done, and we're going to make sure we get the signs of those changes correct. So in this first example here, I'm told I've got a uniform electrical field, 375 newtons per coulomb. I'm told there's a proton in that electrical field, it has a certain charge, plus 1.6 times 10 to the minus 19 coulombs. And I'm told that it moves from the left to the right 3.2 centimeters through that electrical field in the direction of that electrical field. And there's even a little picture down here, what's going on. This would be handy to refer to. In blue is the electrical field lines. It's from left to right. It's uniform. In magenta here, here's our little proton, its charge, its mass. It moves from this initial location over here on the left, A, to this final location over here on the right, B, in the direction of the electrical field. And it moves a distance that is 3.2 centimeters. And so we've pictured all of that. And in addition, something that we weren't told in the question, I've added to the sketch, and it's the fact that as the proton moves from A to B, from left to right, there's an electrical force because it's moving in an electrical field, and that electrical force size is the proton's charge times the strength of the field. And because the proton's positively charged, that electrical force is in the direction that the proton is moving from A to B. So the question asks us 4 things. What is the potential difference between the initial and final locations? What is the potential energy change between the initial and final locations? What is the kinetic energy change between the initial and final locations? And what is the work done by the electric force on the charged proton as it moves from A to B? Now, all these things are related things. They're all related to energy perspective, and how energy is being transformed as the proton moves from the left to the right. So let's go ahead and answer these items. So here's my solution to the problem, the 4 parts of the problem. But before I work through the numerical solutions, I just want to kind of qualitatively describe whether the potential change is positive or negative, whether the potential energy changes are positive or negative, and whether the work done is positive or negative. And to do that, I want us to recognize that for this electrical field that stretches from the left to the right, there must be some source of the field lines over here on the left, a bunch of positive charges. And there must be some endings for the field lines over here on the right, a bunch of negative charges. And so, although I don't really know the exact arrangement of the positive and negative charges on the left and right, I do know that there must be a bunch of positive charges on the left and a bunch of negative charges on the right. Now, that's going to help me think about physically what's going on here. See, the proton is a positive charge. And so, for example, that proton will be attracted towards the negative charges on the right-hand side, repelled from the positive charges on the left-hand side. So regarding the potential, as the proton moves from A to B, does the potential increase or does the potential decrease? Well, when we go from A to B, when the proton goes from A to B, it's moving away from the positive charges, which are a mountain or a hill of electrical potential. It's going towards the negative charges, which are a valley or a well of electrical potential. So it's going from the hill to the valley. The electrical potential is going to decrease. So the electrical potential is decreasing as you go from A to B. What about the work done by the force? Work done by electric force? Well, the proton is moving left to right. The force is left to right. So force and motion are in the same direction. And so if you think about that equation for the work done by a force, that force is transfer energy, that equation was force times distance times the cosine of the angle between the motion and the force. And in the case of the force and the motion being in the same direction, you do positive work. The force is doing positive work. That means it's transferring energy to the proton. So energy is being transferred to the proton by the positive work. That means that the proton's kinetic energy is going to get larger. The speed is going to grow. And the potential energy is going to decrease because that's where the energy is coming from. Remember the kinetic energy and the potential energy piggy banks. What we're doing here as the proton moves from the left to the right is that we're increasing the joules in the kinetic energy piggy bank. We're decreasing the joules in the potential energy piggy bank. And we're doing that by doing work, transferring energy from the potential energy piggy bank to the kinetic energy piggy bank. Okay, now we've got an idea about the signs of potentials, potential energies, kinetic energies, and work. Let's actually numerically calculate the changes in those four quantities. And that's what these four lines on my slide are. So to calculate the change in potential, that's delta V. I'm using this equation here. This is the equation that told us that the electrical field is the negative slope of the electrical potential. It's just rearranged. And so I'm using the fact that electrical field, electrical potential are related. The electrical potential field is the negative slope of the electrical potential. So that tells me that the change in potential is equal to minus E times the change in position. And I just got to fill in the electrical field strength, the change in position, and that will give me the electrical potential, the change in electrical potential, the potential difference. And it's minus 12 volts. And it's negative, as we said, because the proton is moving away from that hill or mountain of positive charges towards the valley, the well of negative charges. Okay, now the change in potential energy. I'm using this equation here. Where did that come from? That came from how we defined electrical potential difference. We defined it as the change in potential energy divided by the charge. And so I've just rearranged that defining equation for electrical potential differences for an equation for the electrical potential energy change. And then I've just got to fill in the charge of the proton, got to fill in the change in potential. I'm using the first part of the problem here. And I come up with a change in electrical potential energy. What you see there is that's a negative change in electrical potential energy, right? We've kind of rolled down the electrical potential hill, and we've given up electrical potential energy. So we're storing less electrical potential energy. There's a negative change. Now the kinetic energy. The change in kinetic energy will be equal in size, but opposite in sense to the change in potential energy. Where did this come from? This is just energy conservation. If I'm going to decrease the amount of energy in the potential energy piggy bank, that amount of energy will appear as increased energy in the kinetic energy, moving energy piggy bank. So I'm just moving energy around. I'm not creating or destroying any energy. So all I've got to do here is multiply by -1, or flip the sign of the change in energy, potential energy, and that will give me the change in kinetic energy. So it's the same size as the change in potential energy, but it's positive. It grew, the potential energy decreased. Finally, the work done. Well, it was the work done by the electrical force that was moving this energy around. And the work done is equal to the negative of the potential energy change. It's equal to the kinetic energy change. So it's the amount of, the work done is the amount of energy we're given to that proton. And so we're increasing the kinetic energy of the proton, decreasing the potential energy associated with the field. And so that work done is also positive. If you want to think of that problem overall, just imagine that this proton has kind of rolled down an electrical hill like you might roll down a gravitational potential hill. When you roll down the gravitational potential hill, or the proton rolls down the electrical potential hill, it's giving up potential energy. It's acquiring kinetic energy. It's moving in the direction of the force so that the work done is positive. Okay, this is the second example that I wanted to work through. In the last case, we had the proton moving left to right through an electrical field. Now we got an electron moving left to right through the same electrical field. So the only change in this problem from the last problem is that in the last problem, we had a proton, a positive charge moving left to right. Now we've got a electron that's moving left to right. It's the same field. It's the same displacement from the left to the right. It's just now we've got a charge of -1.6 times 10 to the minus 19 coulombs rather than a charge of plus 1.6 times 10 to the minus 19 coulombs moving. We've got to answer the same questions. What's the potential difference between the initial and final location? And then what's the change in potential energy of the electron, change in kinetic energy of the electron, and what work was done on the electron by the electrical force? Those questions. They're all the same questions. So this problem, the only difference is that we got a negative charge rather than positive charge that's moving left to right. So this question I can go through a bit more quickly because we've really worked this question in the last example. And we'll just focus on the differences. Just focuses on the consequences of this being a negative versus a positive charge. It's the same picture down here, right? The electrical field, the field lines in blue, the motion from A to B of the electron. The only difference is that the electron has a negative charge, and as a consequence, look at this field equation here. The electron, negatively charged electron, experiences a force that is opposite to the direction of the field lines rather than in the direction of the field lines. So that's a very important point. A positive charge will experience a force in the direction of the field by the field equation, F equals QE. A negative charge will experience a force opposite the direction of the field lines by the field equation, F equals QE. And that's because, when you plug into the field equation, the field and the charge, you're plugging in either a positive or negative charge, which either keeps the force the same direction as the field or reverses the direction of the force, depending on whether you've got a positive or negative charge. Okay, so here's my solution. Again, before I go through the actual numerical solutions, I just want to say a few remarks about the signs, plus or minus, of the changes in potential, the changes in potential energy, kinetic energy, and work. So again, let's recall that we've got some distribution of positive charges over here on the left that are the source of the field lines, some distribution of negative charges over here on the right that are the ends of the field lines. So in this case, this is a negative charge. It's moving from A to B. So it's moving closer to the other negative charges. It's moving further from the positive charges. The negative charges on the right, they're repelling the electron. The positive charges on the left, they're attracting the electron. That's why the force here is opposite the direction of motion. It's just based on the fact that like charges repel one another. So the electron is repelled by the like charges on the right. Unlike charges attract one another. So the electron is attracted by the positive charges sitting over here on the left. Now, what about the change in potential and the change in energies and the work done? What are the signs of those quantities? Well, let's think about the change in potential. Just like the previous problem, we have a potential hill where the positive charges are, a potential valley where the negative charges are. We're moving from the hill to the valley. And so the potential is decreasing. And it didn't matter for the electrical potential that this was a positive charge or a negative charge. That's completely irrelevant for the electrical potential change. Whether you've got a positive charge or a negative charge is completely relevant, however, for the changes in potential energy, kinetic energy, and the work done. So in the case of the proton, positively charged, the work, the force, and the motion were in the same direction. We had positive work done. In this case, the electron, negative charge, we got the motion and the force in opposite directions. That means that the work done is a negative work that's done on the electron. So we're doing negative work on the electron. What that does is decrease the kinetic energy of the electron, and it will increase the stored potential energy of this arrangement of the electrical field. So all of those three things, the work done, the change in kinetic energy, the change in potential energy, have flipped their sign between the proton problem and the electron problem, between the positive charge problem and the negative charge problem. In the proton problem, that proton was kind of rolling down a potential hill. In this electron problem, you can think of the electron as kind of rolling up the potential hill. The proton acquired kinetic energy, the electron's losing kinetic energy. The proton released electrical potential energy. The electron is increasing the stored electrical potential energy. Okay, so let's answer the 4 questions numerically now. So change in potential is the first question. And again, I'm just using this equation here that comes from the fact that the electric field and electric potential are related. Electric field is the negative slope of the electrical potential. And if you rearrange that equation, the change in potential is the negative of the electrical field strength times the displacement times the distance traveled. Plug those numbers in, I get 12 volts, minus 12 volts. Again, it's a decrease. We're moving away from the mountains towards the valley. And whether we were talking about a proton in this problem or electron in the problem, the change in potential doesn't care. The charge of the particle is irrelevant for the change in potential. It is very relevant, though, for the next 3 parts. So the change in potential energy is given by this little equation here. And as I mentioned, this equation is nothing other than the equation that defined for us potential difference as being change in potential energy divided by the charge of the charge. And so we rearrange that, plug in the charge, plug in the change in potential. We get the change in potential energy. And now this comes out to be positive. So it's because we're storing more electrical potential energy as the electron kind of rolls up the potential hill. We're increasing the store of electrical potential energy. Third question, what's the change in kinetic energy? Well, the change in kinetic energy is equal to the negative of the change in potential energy. That's nothing other than energy conservation, that we can't destroy energy, we can just move it around. We're moving it between kinetic energy and potential energy. So however much the potential energy changes, and it went up, there must be a corresponding same size but opposite sign change in the kinetic energy. So the kinetic energy is going to be the same size, but it's going to be negative. And so the electron, as it's moving from left to right, is slowing down. Its kinetic energy is decreasing as it's decelerated by the force in the opposite direction to its motion. And then finally, the work done, we can write the work done in moving from A to B as the change in kinetic energy, or the negative of the change in potential energy. This equation here is just the idea that forces transfer energy, and the work done is the amount of that transferred energy, and it's the amount that the kinetic energy grows by. That's the work done on the particle or the electron or the proton, and it corresponds to the negative change of the potential energy. That's where the energy came from. And so the work done on the electron is a negative work done. And that's because you can see that because the force is towards the left, the motion is towards the right. And so there's negative work being done on that electron. It's being slowed down. It's being decelerated. Anyway, I hope that problem or illustration might address some of the worries or questions about calculating potential differences, potential energy differences, changes in kinetic energy and work done, and in particular, the signs of those quantities. In this problem, if you wanted to visualize the proton case and the electron case, as I say, I imagine the proton as rolling down a hill, and I imagine the electron as rolling up a hill, just like I could imagine myself as rolling down a hill or rolling up a hill. If I roll down, I'm going to acquire kinetic energy. Positive work is done on me. If I roll up, I'm going to lose kinetic energy. Negative work is done on me.